Okay, so we've learned that atoms are made of smaller particles, but what exactly are these forces, the pushes or pulls between the objects acting between these subatomic particles? Four basic forces are at work every day, or everywhere within the atom. Um, and we're going to talk about each one individually. The first one we're going to talk about is electromagnetic force, and the definition of that is that opposites attract and likes repel. And so you already kind of know about this force, and you didn't even know it was called electromagnetic. But if we look at the nucleus right here with my red protons and my blue neutrons, you see my electrons are a little bit further out, and there's actually a purple arrow pointing towards the electrons. This is showing that the electrons are going to be attracted towards the nucleus because opposites attract. So the negative electrons are attracted to the positive nucleus. But at the same time, this force is kind of bad for the nucleus because it allows the protons to repel from one another. So the protons want to get away from each other and basically break apart the nucleus. And this electromagnetic force is the prime culprit for repelling those protons away. So we need another force that kind of keeps that nucleus together, and that's where the strong force comes in. Strong force keeps that nucleus together because it acts as this, I think of it as like a bodybuilder, like strong muscular arms keeping that nucleus together because those neutrons want to repel so much. So the orange arrows are representing the strong force, and they're keeping the protons together with the neutrons, and they're also bringing everything towards the center. The purple arrows are representing the electromagnetic force. So all this is kind of keeping together. The strong force keeps that nucleus together because as these elements start getting really big, we start going lower and lower in the periodic table. There's so many protons in that nucleus that they want to just totally repel. That's where you start getting radioactivity. You start losing part of yourself as an atom, and that's where the strong force kind of loses the battle. When you start getting that big, the strong force loses the battle. It can't hold that nucleus together, so that's where you start getting nucleuses falling apart, releasing alpha particles, amongst other things, and changing into a different element. Okay, we have two other forces involved as well. We have weak force, and that's involved in radioactivity. This is where you can change a neutron into a proton. Radioactivity, if you recall, alpha decay. The weak force is involved. You don't have to know a whole lot of detail, but it's involved with radioactivity. In certain unstable atoms, a neutron can change into a proton and even an electron. The weak force plays a key role in this change. So that's really all you need to know. And then the last force is the gravitational force. The G-force is experienced by all matter. Everything that's made of matter has a gravitational force. And atoms are definitely made of matter, so they're experiencing a gravitational force as well, meaning that they're attracted to each other. They're attracted. The Earth pulls atoms down towards it. The Earth is made of atoms as well. So four main forces that are that make up the atom. Okay, this next slide is about calculating average atomic mass. If you notice on the periodic table, you've noticed this for a couple weeks now, the mass was given in a decimal. And a lot of you have been asking, what does that decimal mean? And for your atom model project, you were supposed to take one of the isotopes of your element and use those numbers to calculate your protons, neutrons, and electrons. Now we're going to investigate a little bit more on why that decimal is there. Basically, the decimal is an average of all the different isotopes masses that that particular element can have. For instance, chlorine has two isotopes, chlorine 35 and chlorine 37. Now they occur at different abundances on Earth. Most of the time you're going to find chlorine 35 as opposed to chlorine 37, which you're going to find 24% of the time. If we do our numbers, chlorine has 17 protons. So both of these isotopes would have 17 protons. But if you notice, chlorine 35 would have 18 neutrons. So we'll put 18 neutrons there. While chlorine 37 is more massive, it actually has 20 neutrons. So you notice that chlorine 37 is going to be a little bit heavier of element of chlorine. Now, you see the 76% and the 24%. here's how you're going to be able to calculate average atomic mass. Okay, so you need to write these percentages out as a decimal. First, you're going to write the atomic mass, so 35. Then you're going to multiply it by the percentage, but the percentage is changed into a decimal. You calculate that answer, and you get 26.6. You do the same thing for chlorine 37, writing the mass out and then the percentage as a decimal. Calculate that out, and you get 8.88. If you add these two together, you should end up with the same average atomic mass that you see on the periodic table. So you add 26.6 plus 8.88, and you get 35.48. Now I included the AMU because this is a mass that we're discussing, and AMU is the unit that you use for mass. If you look at the periodic table in our class, the average atomic mass is 35.45 AMU, and that's very close to what we got. So that's an average atomic mass for all the isotopes of chlorine. Another example would be uranium. Now uranium has 3 different types of isotopes in the universe. And you notice that uranium-238 is what you're going to find most of the time. Uranium has 92 protons. So all of these isotopes of uranium will all have 92 protons. Now as far as neutrons go, take the mass and subtract the proton count. So you'd end up with 142 neutrons for this one, 143 neutrons for this one, and then 3 more would give you 146 neutrons for the last one. To calculate the average atomic mass, you're going to use the same method. Take the mass times the percentage changed into a decimal form. Now you notice the first 2 are decimals, but that's a percentage. You're going to change it into a decimal form by moving the decimal 2 places over to the left. So for this 0.0055%, you're going to move your decimal over 2 places. So the decimal would actually be 0.000055. That would be your decimal. For 0.72, move it over 2 places. 0.0072 would be the decimal for that. And for the bottom one, you're going to move it over 2 places. 0.992745. So you take your mass times your new percentage that's been changed into a decimal, get all 3 products, then add them together. So let's do that together. So you want to get all 3 products and then add them together. Let's pause the video and see what you get and compare it with my answer. Okay, I ended up getting 237.97. AMU. Now, you don't want to really round. Try not to round for anything. On my periodic table in the classroom, it says 238.03. So we're very, very close, 237.9 as opposed to 238. This is the average of all the different isotopes masses that you can have for uranium. Okay, two more practice problems for when you're at home. One is magnesium. Magnesium has three isotopes. So try this at home, and I'm going to check your answers in class. Try this. Magnesium 24 at 78.99%. Magnesium 25 at 10%. And magnesium 26 at 11.01%. Okay, and one more for your notes. I want to see what your answer is when you come to class tomorrow. Zinc 64 at 48.6%. Zinc 66 at 27.9%. Zinc 67 at 4.1%. Zinc 68 at 18.8%. And zinc 70 at 0.6%. All right, figure out the average atomic mass for the magnesium isotopes and for the zinc isotopes. Let me know how you do. Thanks for your attention, and this would be the conclusion of Chapter 4. We've covered everything in the whole chapter, starting with the history of the atom, and the second section where it was the chart, writing electron configurations, and now we finished it up with forces inside of an atom and calculating average atomic mass. So thank you for your attention, and I look forward to seeing you tomorrow. Thanks. Thanks for watching.